Hey everyone, welcome to another video. And in this video, we will be looking at what is wrong with this circuit. So let me ask you a simple question. Take a long look at this circuit. You have a flip-flop, you have a combinational logic, and you have an AND gate, which is going to a resistor set. On the clock path, you have a clock, which is connected to the flip-flop. It's driving the flip-flop, and you have clock buffers which are going to the AND gates, another input. So you have to realize that this is a sequential circuit, and you also have to realize that the both the inputs to the AND gate are also sequential. So you wouldn't be having like a static output at the AND gates output, which is going to something called as a resistor set, which you can just assume, it's a random path which is going to another set of sequential logics. And this input is also coming from output of some other flop. So take a long look at this circuit and tell me what is the issue with it, right? If I randomly ask you what is the issue with this, you'll just say it's perfectly fine because, hey, take a look at the flip-flop, the flip-flop can, let's say it's a D flip-flop, a buffer flip-flop. You're just going to give the input, take the same output, it passes through a combinational logic. Clock tree buffer is still a combinational logic, so the clock also passes through a combinational logic. And finally, it goes through an AND gate and then goes to a register set. But actually, there is an issue with the circuit. What is the issue is that the time. Here, we are not just considering the random values that we are going to get in the AND gate. We are not going to just analyze the and draw the wave diagrams at the output of the AND gate. We are not here to say, hey, this is going to be a toggle circuit and this is going to be a toggle waveform, and we are just not going to AND the clock and the toggle waveform and then give an output. We are looking at some sort of meaning, because when you see a register set, when you see output from another flop, you have to know that there is some sort of data transfer. And when you talk about data transfer, you also talk about data preservation, rather data protection, or making sure that there is no data loss. So all of these are synonymous to each other. So when you talk about ideas like that, uh, where you get to is the timing, because the timing is something that's extremely crucial. Why I say this is because usually timing is something that we neglect a lot, because we focus a lot on the functionality of the circuit. If I ask you what is the problem with this circuit, you'll immediately say that the buffers are perfect, the combination logic is perfect, everything is connected perfectly, it's a good synchronous circuit. But an actual engineer will want to look into the timing of the circuit, and that is actually where you score, because the timing makes up the logic, the data transfer smoothly. So before I go into that, let's just have a small recap of the pillars of static timing analysis, as I like to call it: setup time and hold time. So what is setup time and hold time? Now, this is a very standard question. And I know a lot of people who just tell the definition immediately. The setup time is defined as the minimum amount of time before the clock's active edge. The hold time is the minimum amount of time after the clock's active edge. But what does it actually mean? That is something that I am more interested in, right? So let's take a look at this waveform. So this waveform is going to shift. This clock is going to shift at a particular place. Now this again, this is an ideal clock, because you will never see perfectly rising edges in practical real life, but let's always assume that the clock is going to be a perfect rising edge, right? So when the clock is rising here, the edge is rising here, what you will notice at the output of the flip-flop is that there is going to be a particular period of time uh, around this clock rising, right? So if you have a clock rising edge here, there is going to be an amount of time around it. Now there is a common misconception, which is that people differentiate setup and hold time as before the clock edge and after the clock edge. No, there is a particular amount of time around the clock edge which has to be preserved, and you call it setup time when it is before the edge, you call it hold time when it is after the edge. That is the only difference. But the preservation of data has to be around the rising edge. You have to make sure that the data is not lost. How do you do that? You make sure it is the same when the transition is happening. So that is the idea of setup and hold time. So once we have that clear, we can move into the actual question of this video. So the actual issue with this circuit is that there is a violation. Now, I spoke about setup and hold time. I spoke about why we need timing analysis. Now, let me talk about violations. So, there are two types of violations that are concerned to us as VLSI engineers. One is the setup violation, the other one is the hold violation. So, when I say setup violation, it is not that different from hold violation. So, let's talk about a timing violation, similar to how we saw with the clock, right? So when a clock is shifting from uh, in the rising edge, from when it is going from 0 to 1, what you're basically doing is that you are just making sure that this transition is smooth, right? You are not doing anything separately for setup and hold time. You are just making sure that the setup time is the time that it is going to be preserved before the rising edge, and hold time is the time it is going to be preserved after the timing edge. But actually what you're doing is you're just preserving the data around the rising edge. So similarly, the violation that is going to happen, let's say at this point, is not that complicated. It is only based on the data flow path and the clock path. So when I say, it's only concerned with the two of these, a question might arise. If it's that simple, why do we have so much complications? Right? But this is not the mathematical way to look at it. I am just explaining how to visualize a violation, because that is the toughest part of any circuit, right? If you don't visualize it, what is the point of writing hundreds and hundreds of circuit equations? Because at the end of the day, you are going to write the equation wrongly if you don't understand what's happening. So this path is called as the data path because the data flows in it, which is self-explanatory, and this path is called as the clock path because the clock flows in it. Now, at this point, let's assume this point as our cutoff point, or let's say as our reference point. Now, the data will travel through from the input to the flop input to the flop output through the combinational logic delay, and then reach this point, let's say A, right? Again, let's say there is a point B on the clock path. The clock will start from the clock itself. Then it will move towards the buffers. There are three buffers, which are tree buffers. Then it will move towards the point P. So now you have to realize one thing. The clock will have a delay on its own, which is going to be characterized by its path here. Now there will be wire delays, which we might neglect or which will be given in the problem. There will be buffer delays, and finally it will reach point B. There will be flop to flop delays for the data path because it is coming from here. It will face flop to flop delays, and then it will face combinational delay, and then it will come to point A. So this is going to be the path that is going to be taken by the data path, and this is going to be the path taken by the clock path. It's very simple. The hold violation arises when the clock arrives before the data. Now, that doesn't mean the setup violation is when the data arrives before the clock, because there can only be two scenarios. The clock is arriving earlier or the data is arriving earlier. The problem is when the clock arrives earlier, because let's say the clock arrives earlier. Now, if there was another flop here, which is not present, but if there was another flop here, what will happen if the clock arrives earlier? The data itself has not come yet, but you have the clock, and the clock will have to go through a positive edge. What happens here is that you are sending across data which is random, which is bullshit. You are not sending the actual data that has to come through to the next stage of the flop. Rather, you are sending some random data here. But let's say the data arrives before the clock and the clock is going to drive the data later. It is great, right? You have no issues. So this, the first thing that I told you is called as the hold violation, because here the clock is arriving earlier and the setup is not there. Second part is where I'm going to explain the setup violation. So we've seen the hold violation. Basically, the data is not coming before the clock. But there can be a scenario where what happens is that in the flop, in the setup violation, you face something very similar to what happens in the hold violation, except the culprit is with the first flop. Now let's say that you have a flop to flop delay, but let's say that there is some sort of delay in the setup path, setup time. So let me just pull across this clock. So let's say this setup time, the time in front of the uh, rising edge, rather the time you need to keep it stable before the rising edge is too high. Let's say that the time is going to be held stable, it's going to be very high. What happens here is that how much ever fast the clock is going to switch, the correct data will be taken by the first flip-flop, right? But let's say this setup time is extremely small. So rather than having, let's say, the setup time here, I have the setup time here. So what happens here is that if at all the data is going to change here and the clock takes this much time to rise, what happens here is that an incorrect data is going to be latched at this end itself. So incorrect data is going to be passed outside the flop, pass through the combinational logic, and then come to this point. Now here you will be facing incorrect data, but the culprit is at the beginning of the first flop. Whereas for hold violations, the data is passed smoothly, but you are facing wrong data because the second flop messes up. Basically, the clock reaches faster to the second flop. So wrong data is passed to the output of the second flop. But in the setup violation, due to the setup time being very less or the clock period being very less, what happens is that wrong data is latched into the first flip-flop's input itself. So what happens is like a series of mishaps and you will finally get the wrong data. So this is going to be your setup and hold violations. Okay, so coming to the question here, look at this particular circuit and tell me if there is a setup or hold violation. I'll give you some 10 to 10 to 15 seconds. Okay, so let me explain what is wrong with this circuit. Now you know what is a setup violation. It is caused due to the small setup time or the clock period issues with the clock, and it is caused in the first flip-flop's input. Hold violation is caused due to the fast nature of the clock period or the clock path rather, and it reaches before the data path. Looking at this circuit, what can you infer? uh, Let us say you have a data path which is going to be slower than the clock path because you have clock tree buffers, right? So the data is going to come after that, only the clock is going to come. And what happens here is that the data arrives early, clock arrives late, but here is a problem. You would argue that there is no hold violation, why are you crying? But the problem arises when this buffer causes a very large delay. Why I'm saying very large delay is because the clock is going to be transferred to the data at a particular speed. Now let's say the clock output is going to be at a particular period of time, but the buffers are at a different period of time. What happens is that the clock skews at every particular, let's say, period of time. And what happens is that if the data happens to be changing at uneven periods of time, the wrong data will be latched due to the late nature of the clock. Now there is a name for this, obviously, which is the reason you clicked on this video. It is called as clock gating errors. Now it is not the data path's fault that this hold violation is happening. You don't see the data path appearing slowly and the clock path appearing faster and the wrong data getting latched. But what happens is that due to this delay, you are losing a little bit of time every clock period after clock period. It goes to a point where after a few clock periods, the clock is reaching the point B before the data reaches the point A and you lose a clock cycle in the clock period. This is called clock gating hold violation. That is why it's called as a hold violation. You are not facing a hold violation in the beginning, mind you. This is something called as a virtual hold violation that happens due to the clock gating effect. That happens due to the buffers present in the clock path. I hope I've explained this phenomenon slowly because I've built up from the setup time, whole time, setup violations, and I finally explained what is happening here. Uh, please put comments if you don't understand or something is wrong in my video. Please comment on it and I'll correct it immediately. I'll provide a clarification. Thank you for watching.